Thank you for the introduction. I have no financial interest to declare. So last year, our group showed that it is possible to use machine learning techniques to map otherwise intractable microstructure features, such as the axonal permeability, using a random forest-based computational model. The axonal permeability is directly related to the average time, tau I, that a water molecule spends inside the axons, which is also known as the intra-axonal exchange time. Since the interaxonal exchange time is inherently difficult to measure in vivo, we need to use an alternative database with accessible ground truth labels to use for our supervised regression task. And so, the paper introduces, as part of their framework, the first step, which is to use a diffusion simulator to generate a database of diffusion-weighted MR signals and their corresponding realistic tissue substrates with known ground truth parameter values. We then use this database to train a machine learning algorithm, which is here random forest, which constructs a mapping between the diffusion-weighted MR signals and the microstructure features of the tissue substrates. Once we have our trained machine learning algorithm, we then feed in as an input the diffusion-weighted MR scans and produce parameter maps of microstructure features, including the interaxonal exchange time. A commonly known limitation of working with simulations is that they cannot always fully replicate all the physical phenomena in the real world. And so here, for example, we show on the left an electron microscopy slice through white matter, while on the right, we show an example of a simulated tissue that we use for training. So a simple visual inspection reveals differences between the two. If we look even closer at the experimental versus the simulated data, we see that for some settings of the imaging protocol, such as the first two shells, there is a good match between the experimental and the simulated data, while for different settings of the imaging protocol, such as the shell on the last line, there is a bigger gap between the two. So there are several ways to address this partial mismatch. One way to do this would be to use for more realistic simulations for training. And our group is currently working in this direction, as we have shown in the validation session this morning. Another potential way to address this problem is by moving towards a neural network architecture to take advantages of the recent advances in the deep learning field. So moving in this direction constitutes the aim of this work, which introduces for the first time a neural network for axonal permeability estimation in white matter tissue. To generate our simulated training database, we use a PGSE imaging protocol with the following settings, which match the experiments in our data, in combination with the Camino diffusion simulator, to generate a database of 11,000 diffusion-weighted MR signals, each corresponding to a unique tissue substrate with known ground truth parameter values. From each substrate, we keep as labels during training 3 microstructure parameters. And to match the experimental data in our work, we add Raytian noise with signal-to-noise ratio 30. Additionally, following the pipeline introduced in our neuroimage paper last year, we extract an equivalent rotationally invariant database by extracting diffusion tensor and spherical harmonics features from the signals database. We will then test the performance of our models on both equivalent databases. So this constitutes the first step in our model pipeline, which is followed by implementing a feed-forward, fully connected neural network using Keras with TensorFlow backend. This network has 3 hidden layers with ReLU activation functions, and it is trained using stochastic gradient descent with momentum and dropout. We use an 80-20 train validation test split, and we train 2 networks, one for each of the 2 databases presented earlier. Once we have our trained neural network, we provide as an input the in vivo data, which is formed of 8 healthy wild-type mice, scanned on a Bruker 11.7, and then we produce parameter maps of the 3 microstructure features kept as labels, so the interaxonal volume fraction, the interaxonal exchange time, and the intrinsic diffusivity. Finally, we compare the performance of our neural network model with the previously established random forest. So here are the results with the performance in the noise-free simulations, tested on the same previously unseen test set for both random forest and the neural network. We observed very strong correlations between the ground truth on the x-axis and the predictions on the y-axis. For the exchange time, we noticed that the neural network outperforms the random forest with higher correlation coefficients and accuracy. We obtained a slightly better performance when using the signals database versus the features derived from the signals database. For the other two microstructure parameters, we observed no difference in performance between the random forest and the neural network for both databases. We just show here for easiness the results using the signals database. So here are the results with the performance in the noisy simulations. We see that the noise affects the correlation coefficient and the accuracy of the predictions for the exchange time. However, the neural network continues to outperform the random forest. The exchange time is still quantifiable with a consistent positive correlation. And we also noticed that the noise closes the gap between the predictions using the signals versus the features-derived signal database. However, we got a slightly better performance when using the signals. For the other two microstructure parameters, we continue to observe no difference in performance, significant difference in performance between the signals and the features database for both models. So here are the results from the in vivo data. Here we show the parameter maps of the corpus callosum of one of the 8 mice, here using the random forest predictions, and here using the neural network predictions. We observed that for both models, for all parameters of interest, the predictions are within a plausible range. Here are the results with the probability density distributions of the predictions for the corpus callosum of the 8 mice. In red, we have the predictions of the neural network, and in blue, we have the predictions with the random forest. So looking closer at these, we see that the average neural network estimate for volume fraction is 0.44, which matches closer the average estimate from the ex vivo and immunohistology data from the myelinated axons of the corpus callosum of the same mice. For the intrinsic diffusivity, literature estimates for this parameter show values around 1.2, which in the corpus callosum of the mice, which match closer the predictions of the random forest. Finally, looking at the exchange time, this is an inherently difficult to validate parameter in vivo, but several studies suggest values between 0.3 and 0.6 seconds. So taking all this into consideration, we can say that the neural network improves the predictions of important brain tissue features using diffusion-weighted in vivo data. To conclude with, we have here introduced for the first time a neural network for axonal permeability estimation. We have then showed that our neural network outperforms the previously established random forest in simulations of the white matter tissue. We have then produced parameter maps of mice corpus callosum using in vivo data, and we show that there is a good match between the predictions of the machine learning models and the expected values, with the neural network providing estimates closer to the expected values. Just briefly touching on future perspectives, we are currently working on developing a model that incorporates multitask transfer learning techniques to further address the gap between the simulated and the experimental data. I would like to thank you for your attention, and thank you to my collaborators for the help.